Okay, hi everyone. First I want to make some remarks about the organization of the course. We still have 3 lectures left, so I want to give you some kind of general idea of what you can expect. The first that will be today will be more about geodesics, and we will discuss more the minimizing properties of geodesics in terms of length. Next time we discuss what is called the fundamental lemma. That was for surfaces, for curves, it was reconstructing the curve based on some curvature and torsion information. And the question would be, how can you, at least locally, maybe reconstruct the surface out of some other data? And then the last lecture in the new year will be about what is called the Gauss-Bonnet theorem, which gives you some kind of allows you to say how much curvature is total curvature a surface has in terms of some other quantities. So that's roughly the plan. And for the homeworks, we only have 1 sheet of homeworks left. So the coming homework will be the last sheet for the term. That will be, you have to hand it in at the 27th of December. And then afterwards, I will post somewhere early next week, I will post a test exam that you can do. You don't have to do the test exam. You can just solve that by your own. But if you want to add feedback, you can hand it in, and then a teaching assistant will look at your solutions and point out okay, here you have a mistake, and then you still get feedback before the exam. The exam date will, most likely you will get an official announcement at some point, or maybe you already did it. I think it will be at the 8th of January, at least currently that's my information. Do you have any questions concerning the general structure and organizational? Yes. Wait a second, I have to. Yes. So you're allowed to bring 1 sheet of paper, like this one. You can write it on both sides. Please, really, just 1 sheet of paper, not glue 2 together and then tell me that's still 1 sheet of paper. So really, just 1 sheet of paper. You're allowed to write as small as you want. Usually, it's a trade-off. If you write very small, then you have put a lot of information there, but then you look in your exam, which is the formula, and then you can't read it anymore. So it's that's up to you. If you have a very tiny handwriting, then you can put a lot of information there. You can put whatever you want, formulas from the lecture, formulas from books. It's totally up to you what you put in there. You can also put definitions, proofs, whatever feels is something that helps you to survive the exam. Generally the exam will be a little bit like the homework, like the first part of the homeworks, not the exam qualifying, but the graded ones. From the level of the problem, there will be some problems that will be the first part will be that you have to quickly say if a certain statement is right or not right, and then you have to give a short justification, saying every geodesic has constant speed, and then it says less yes because, and then you do 1-line calculation or something like that. So it's things like this. Very basic results that test a little bit that you know the theory, but also can apply that. And then the rest of the exam will be mostly the normal homeworks. Are there any other questions? yeah, you're not allowed to use any calculator. In principle, it would be possible to have like a basic calculator, but then I have to say like what is basic and not like programmable, and then you put like formulas in there. So just like no calculator, and you don't need a calculator anywhere. It's not about the numbers, it's more about the formulas and your understanding. Okay. Any further questions? Awesome. Then let's start with the fun part, namely about geodesics. And the topic will be that geodesics are the shortest paths. And it's a slogan that you read often, but as we will see it, you need to be a little bit more careful sometimes. But that's like the slogan for the next time. So, so what we have seen is like in the plane, what you know from experience is that the straight line is the shortest connection between two given points. So if I give you 2 points in the plane, say P and Q, then you know if you have to find the shortest path, that will be just the straight line that connects both of these points. So the question would be, what is now the similar answer on the surface? Where I give you 2 points on, say, on the cylinder, say like this point here and this point here. What is the shortest path? Is it like going like more kind of like this way, or do you go around it? So that what is the shortest path between 2 points on the cylinder, for example, or on way more complicated surfaces? So that's the question that we would like to answer. And for surfaces, we already saw that geodesics are the natural generalization of a straight line in many ways, and that the vectors are parallel, and they are like the acceleration is normal. So in some way, the geodesics are the generalization of a straight line. So the question would be, are geodesics the shortest connection between two given points on the surface? So that's the natural generalization, or question that we would like to ask. So what does this actually mean? In order to write down what it means, we consider the length of a curve, which is probably maybe, don't know, do I want to normalize it? No. So we look at the length of a curve, say defined on the interval, then this would be this integral of the curve as a curve. And here, of course, we use the first fundamental form of our surface to measure the length of the curve. So that's the function. And what would it mean that the shortest path between two points would be given the question that we have, given 2 points, is the path C that minimizes L of C among all paths that connect P and to Q a geodesic. And vice versa, if you have a geodesic, is that automatically a minimum of that function? So that's the question that we would like to answer. So how do we say that something is actually a minimum of this function? For that we use like an analogy from like normal calculus. So assume for a moment that f is a smooth function on the surface, and we would like to find the minimums of S. So f would be then, of course, this linear functional as an analogy. And find the minimas So how do you do that? How do you find like the minimas of a function on a surface? Or in some open subset actually. It doesn't matter too much. Defined of an open subset. How do you like find like the minimas of a function? What do you do? Yes. So you have a function, and you would like to find these points, perhaps also extremas, so not just like the minimas. If that's f, then what you do to find these points is you take the derivative of f. So that's usually the step number one, is like find the zeros of the derivative. And in our case, that would be a TMF. Okay, so how do you calculate the derivative on a surface? Is so we need to find a point M such that for any curve let's call it gamma instead of C to not confuse it too much with the C over there, which is a curve in S starting at M we have namely that the tangent map of f in the direction of gamma, which would be a gamma at the 0 point, we want that to be a 0 because the derivative needs to be a 0. So whenever you change f slightly in whatever direction, you get 0, so that you're in a minima or maybe in an extrema, more general. So how do you calculate this if you have a curve? Is by using the normal theory, where we say you have f, and in f you insert your curve, and then you take the derivative at epsilon equals to 0, where epsilon here is the like the number or like the coordinate in the interval. So that's how you calculate these extremas for a function on a surface. By just taking a point, you have to find a point where then if you have any curve of that m, this expression that you get here has to be 0. So the idea is now to use the same kind of strategy, but instead of having f to be just like a function on a surface, like here we have f just like some function on a surface, but what we would like to do now is actually apply that to L, where we now have like where we allow to vary the C. So that's not like a surface in any sense. It's like the C can be very has a lot of information at every point you can change it. So it's like there's a lot of data. It's not two-dimensional. So it's not really like a surface, but like the same strategy works, namely that we find like a small variation of the point where we have m, and we go in a certain direction with gamma. So we change our point slightly, and then we look at like what the function is doing under this slight variation. And the same thing we can apply to this L. So apply same ideas to the function, which is the length. So we have L, which is defined as all paths that connect P to Q, and then it gives us a real number, so that's just the length. So what we need to do, if you now consider this one as like the S over there, like as we need to find a variation of our original curve, and then we evaluate L along these variation. So we need to, the step number one would be, we need to see what are variations of a curve. So the same way that up there we had like a variation of a point, but now we need to say like what is a variation of a curve. So that's the first point, and sorry, let me see if I can make it less. Let's hope now it's a little bit better. Okay, so we need to say what a variation of a curve is. So in a picture, you can think of that we have P and Q, two fixed points, and then we look at one curve that connects these 2 points. Now we would like to say what the variation of that is. So you may say you fix like the endpoints, and then you have a curve that looks a little bit like the original curve, but like changes. So it might look like curves like this, where you have like they change depending on a parameter. You get like different kind of curves instead of just having one. They might, of course, be a so the definition to make this mathematically precise is the following. If C to S is a curve from P, which is C at 0, to Q, which is C of 1, then a smooth variation of C is a family of curves which we call C of epsilon, depending on some parameter, beta epsilon, and say epsilon is allowed to be in the interval 0 to 1, such that they can be like connected to, or to be put like in a smooth map. The map, which is sometimes called C with a hat, is defined as like the curve of 0 to 1 and 0 to 1. So here it's the parameter of t, and here it's the parameter of epsilon, and then it gives you a point in the surface which is defined as follows, that we have C or t of epsilon is we take the epsilon curve and evaluate it at the time instance t equals to the given time. So let's take the example that we have our curve here, which we call C of epsilon. So that would be one instance of this red curve. And then if you give me a time instance, then this one would be a C epsilon of t, which we can also write as a C hat of t of epsilon. So this map that says like, okay, like we change slightly the curve, and then at which point are we, if you give you epsilon and a t, that map needs to be smooth. Smooth. And of course, we would like to say that for epsilon equals to 0, that should be the original curve. And C of epsilon at epsilon equals to 0 is just C. So that means if you rewrite it in terms of this map, means that at epsilon equals to 0, we have the C equals to just C of t. So that would be saying that you really approximate or like vary like the curve C for epsilon equals to 0, and then you change slightly your epsilon, you get like a whole family of curves. So that's what is called a smooth variation of the curve C. So that's the step number 1. And then we need to say like what is the tangent vector. So that would be up here we have, so in some way, what we now clarified is what this guy here is. That's variation. So here it's the variation of the point M, but here up there we have like now the analog, which is the variation of a curve. So that's something that depends on epsilon and changes the curve. But now we also would like to say what this guy is, namely the derivative with respect to epsilon at epsilon equals to 0, which would be the tangent vector. So that's the second ingredient. Second one would be the corresponding tangent vector. And for that, we have for a variation C epsilon of a curve C. Oh, sorry, one more terminology. Maybe. Okay, sorry. One more terminology is like if in this definition, we are allowed to change the endpoints. Like there's nothing said about what happens to t at t equals to 0 or t equals to 1 if I change the epsilon. So the picture up here looks like they start all from p and go to q, but this definition also would allow like that my family have like p and q. And we get such a family. That would be also a variation of the original curve here. But in this case, the endpoints would change as well. So sometimes you would need to allow changing endpoints variations, and sometimes you don't. So that's like an extra definition saying that if C of epsilon at 0 equals to the original point and C of epsilon at 1 is also the original point, then C epsilon is said to be a variation with fixed endpoints. So that's an extra condition. So now back to the tangent vector. So that would be the derivative in the epsilon direction at epsilon equals to 0. So for a variation C of epsilon, what is called the variational vector field, and that's usually denoted by V of t, is given as we take the expression of C of epsilon depending on t. So we fix the time instance, and then we change the epsilon and take the derivative in epsilon direction at epsilon equals to 0. And the notation makes sense. It's indeed a vector field, namely a vector field along the curve. a vector field along the original curve C. And if C of epsilon has fixed endpoints, then V at 0 equals 0 and V at 1 also equals 0. So the way you can picture that is the following. So we have our original curve C. Let's say we do something with fixed endpoints. And then we choose a variation, which would be like other curves that go from P to Q, and they depend on some parameter. And now you go to a point, say C of t, and then you get corresponding points here, which live on these curves C epsilon. So that would be C epsilon of t. So here you have now a curve that, like, says for every epsilon, we have now like a line that starts here and it goes in this direction. So that gives you a curve, and that curve is a curve in S, and then you take the derivative of that curve. That gives you a vector which sits here at that endpoint. So that would be then V of t. And now you can do that at every point. What you get is a vector field that points along the curve, and that gives you some infinitesimal deformation of the curve. That it's like a vector field, and then like it says like infinitesimally how much do I deform the curve in that certain point and direction. Okay, so now we have all the ingredients for the following proposition. And it turns out that we need also a related expression or functional, and that's the energy. It's the energy of the curve. So it's in some way like the kinetic energy if you're coming from physics, and that's defined by E of C. It's very similar to the expression that we just had, where we take the length of the tangent vector, but then we square it instead of just taking the linear case, and then we integrate all of that. So that's the energy or kinetic energy if you think of the curve as like a particle moving, so without any influence of a potential. So it's just like the free kinetic energy. And as we will see, in some ways, it's usually better to actually look at E of C instead of at the length, because the energy has like slightly better properties. So now we come back to this blackboard over here. What we want now is we apply. We want to find the minimizers of L. So that means the points where if you plug in a variation of the curve, then epsilon goes to at epsilon equals to 0 has to be 0 for all kinds of variations. And that's the statement of the following proposition. The following proposition says that if C of epsilon is a smooth variation of a regular curve C, so with fixed endpoints, so the variation is allowed to have only fixed endpoints. Then you have the following formulas. What we want to do is we want to calculate d of the epsilon at epsilon equals to 0 of the length functional applied to a curve that depends on epsilon, and similarly d of the epsilon at 0 of the energy functional. So that's very similar up here. It's exactly the same kind of formula. We have d of the epsilon of the function that we want to minimize. In this case, it's the length and the energy of a variation. It's exactly the same kind of principle. And then to find the minima, we set, in the next step, we will set it to 0. But first, we have to calculate what these expressions are. And the proposition says that perhaps it's the best to start with the energy. It's a slightly simpler formula. Namely, here we get 0 to 1 of the first fundamental form of the variation vector field paired with the covariant derivative of the curve. And then we have to integrate that over tau. So it gives you the first inclination to say, like, oh, there is something that depends on the covariant derivative of C. So that's like the connection with geodesics is like appearing there already. And the formula for the length functional is slightly more complicated. Namely, we get that it's similar as we have here, b of tau, and the covariant derivative of the tangent vector field. And then we have to take the quotient by the norm of the tangent vector field and then integrate over tau, where this v of t is the variation of vector field. Of C epsilon. So it's the epsilon derivative at, in the terms at 0. So that's the formulas that we would like to calculate. And I will only give that formula or the calculation, the derivative derivation for the energy, because it's a little bit more simple. But the same ideas apply to L. So we would like to calculate what is d of the epsilon of the energy functional of 0 of the curve. So what we do is we write just the energy, and then we interchange the derivation of the epsilon with the integration. So what we end up with is that we have 0 to 1 over the partial integration at epsilon equals to 0 of the tangent vector, and then we just insert C of epsilon here in this expression. So we get C dot of epsilon in the tau direction, and then we take the derivative in the epsilon direction. So that's the first step. So let's do that. Here we can use that it's this expression over here is just I of C dot epsilon of tau, C dot epsilon of tau. So we can calculate the derivative on epsilon. We have to plug that in these different terms over here. And we already saw last time, that was one of the formulas that we had, that if you take the derivative of something that depends on is in the first fundamental form, you can do that, but then we have to do the covariant derivative of each of these slots. So what we get is that it's 1/2 of the integral, and then we can plug in the variational covariant derivative at epsilon equals to 0 of the curve C of epsilon at tau, and then we get C dot at epsilon equals to 0, and that's just the curve itself. So that's C dot. And then we get a similar expression, but this time we take the covariant derivative in the second slot and have to replace the first with the. So we have, in this case, C of tau, covariant derivative, epsilon equals to 0, C dot epsilon. And then we integrate all of that over tau. So now we are happy because actually both of these terms are the same, because the first fundamental form is just a dot product which is symmetric. So we can interchange that and get 2 times the same. So this cancels with the first 1/2. So what we get is that the first covariant derivative at epsilon equals to 0 for of this expression d tau. Okay, so now we compare this equation to the equation that we want, and we see that here we have the covariant derivative of the tangent vector at epsilon, but here we want actually the covariant derivative, or like the derivative in epsilon direction of the curve in itself to get the variation vector field. So here, this is nothing else than d dt of the curve at C epsilon of t at t equals to tau. So now last time we had actually found that you can exchange the if you have such a variation for epsilon and t, if you have 2 derivatives, then we can change the order and replace one of them with the covariant derivative. So we can exchange the epsilon and the t derivatives. So here we used last time the formulas for the derivative, and here we also used some formulas for the derivative. And what we obtain is that we get the covariant derivative with respect to t now at t equals tau. And now we change the epsilon variation goes inside and hits the c of epsilon of t, but that is just by our convention. It's v of t. And then here we don't change anything. So that's, we just changed the epsilon and the t derivatives. And now the next step is, over here we have v of tau. So that's already almost what we want, except that here we have ddt too much. We take the ddt there. So the idea would be to take the ddt out, to something that is like essentially a partial integration or integration by parts, to get the v of t without the derivative. So what we get is then like essentially an integration by parts, or what we do is we take the ddt out at t equals to of tau of the expression where we have c dot of here. So we have that expression. Now we take ddt of this. Then by last time's formulas, what we can do is we take the ddt inside, and we have to do the ddt in the first part and in the second part. If you look at the first part, what we get is exactly this kind of expression. But then we get a second summand, which we have to account for and we have to subtract. So in this case we have to take the variation and derivative, the covariant derivative tau of the curve c of t. And then we integrate that. So now nice thing is, here we can now use the normal fundamental theorem for this first integral to calculate. The first thing would be at the endpoints, so that would be v of 1 at minus the integral where we have v of 0. And then this last integral just remains. So now we use the fact that in our theorem or in a proposition we said that c of epsilon has fixed endpoints. So that means that v at the endpoint 1 is 0 and v at 0 is also 0. So the both terms like vanish because of this assumption, and what we end up with is that we get like this integral, and that's exactly the claimed formula that we have over here. So the proof for L is exactly the same. Okay. And one remark about this proposition is that the regularity of C